All right, welcome. We are going to start a new unit today. It's Unit 6. It's on stoichiometry. Man, the stoichiometry is boringly stiff. Maybe it would help if I had arms and could read more than the first page. The Easter Island statues, if you don't know what this is. Okay, so we are going to go mole-to-mole today with balanced equations. So we're going on with what we learned in the last unit. I looked at some of the multiple choice tests. We have some 100% on them. Yay! I'm excited. I can't wait to get the written part corrected for you so that you can see what your grade is. I'll get that in as fast as I can. Oh, I'm hoping it's more yay. We'll see. Let me get it graded. We're going to be doing 6.1 today, but we need to be handing in. So we're going to be working with balanced equations and going on with that. So a balanced equation is like a recipe. It tells us exactly how much of each thing we need and how much is left over. So if I have a recipe to make chocolate chip cookies, I might have a bin of flour, a bin of sugar, a couple bags of chocolate chips, some eggs, but I'm not going to use all of it. I'm going to have some leftovers. And there's going to be something that's going to be what we call my limiting reagent. That's the most I can make because that's all I have. Maybe it's my eggs, maybe it's my flour. I'm going to run out of one of them. And in order to follow the recipe, I've got to just use that amount. So, stoichiometry is just a fancy word to say, what am I going to run out of? That's my limiting. What am I going to have too much of? That's my excess. Okay? With fancy words. So, stoichiometry is a study of qualitative relationships between the amount of reactants and the amount of products that are formed. In other words, how much of the reactants can make how much of the product. So just sort of like the cookie analogy. You don't have to use these exact words. Make sure that you are using words that you understand. The cookie analogy probably is easiest for me to remember, but if I'm making stroganoff or if I'm making a spaghetti sauce and I want it to turn out just like Grandma did, I better follow her recipe. Okay? Or you could do ham-fried rice or whatever. There's a little bit of leeway with ham-fried rice and spaghetti sauce, but not so much with cookies or cake. Or even breads. I don't do so good with breads. I make good hot and tucks of breads. After many, many years, my husband finally says it's okay to buy good breads. Alright, so get it in your own words. Just stoichiometry makes you sound smart. Basically, it's just a recipe. Okay? Alright, we okay to move forward? Alright. Maybe. There we go. So, you can also talk about making cheese sandwiches. If you have 10 slices of loaf bread, 10 slices of cheese, how many sandwiches could you make? If you're doing grilled cheese sandwiches. I can make 10?
Oh,
5. And what would be left over? Nothing for me because I like 2 pieces of cheese on my grilled cheese sandwich. But if you just did 1 slice, it would be 5. Okay, so my limiting would be my cheese. My excess would be my 10 slices. I would actually run out of that. Actually, sorry, backwards. Slices would be excess. Loaf would be limiting. That's what I would run out of. Okay, so really quickly, there you go. We can make up how we're doing here. So if we wanted to make 7 grilled cheese sandwiches, we need 7 times 2 pieces of bread. That means we need 14 pieces of bread. Okay? So it's just, stoichiometry is just figuring out how much you need of each thing, okay, to do the recipe. Okay, if I'm doing chocolate chip cookies, it gets a little bit more crazy, right, because there's more ingredients. But if I want to make 24 cookies and the recipe only makes 12, I just double the recipe, right? So I have twice as much of everything coming down. Are we okay? And I don't know why this subtitle thing is going on, that's new. All right, so what do coefficients mean in a balanced equation? They're just the ratios. So for every 1 nitrogen, I need 3 hydrogens to make 2 ammonias. Okay?
Wait, what are they?
They're just telling me how much of each one I need. So this is another way to put it. 1 nitrogen molecule plus 3 hydrogen molecules makes 2 ammonia molecules. Okay, it's just another way to state it. They're the ratio or recipe for the chemical reaction. It's just another way to say it. And if you think of it as a recipe, it makes it a lot easier to do the calculations that you need to do. To figure things out. Okay, so using this balanced chemical equation, how many moles of hydrogen are needed to react with 2 moles of nitrogen? Well, my ratio is 1 to 3. So if I have 2 moles of nitrogen, what am I going to need? I have 2 moles here. How many of these am I going to need? 2 moles, yep. And if I didn't know, I could set up my factor label here. And I could say for every 1 mole, there's 3 moles. Moles of nitrogen go out, and I end up with 6. Now I'm using the simple one so I can show you the setup so you know how I got it. So I'm just using the number out in front as the ratio. Okay? So that's where the 1 and the 3 came from. Right? Okay. So 2 moles of nitrogen need 3 moles of hydrogen. That means I'm going to need a total of 6 of them to make 4 moles of ammonia. Okay, so you need to see it visually, that's what's going on. Okay, so how many moles of nitrogen, this time we're looking for this, moles, are needed to react with 3 moles of hydrogen? Should be able to do this quickly. 1. Right? We can go through and we can set it up, 3 moles, 1 mole, 3 moles cancels, and we get 1 mole. So we can also look at it visually. I have 2 moles, 3 moles, I'm going to get 2 moles of ammonia. Okay, so how many moles of ammonia are produced when I have something that's not easy to dispute? 2.5 moles, so I'm starting with 2.5 moles of ammonia, of nitrogen. And I have excess, meaning I have lots and lots of hydrogen, so I don't need to worry about this. How many of these am I going to get? Okay, so we set it up the same way. Start with what you're given, 2.5 moles of nitrogen. We're going to put on the bottom what's in front of the nitrogen because we want to get rid of it, which happens to be 1, right? We're going to put what we want to go to on the top, which is ammonia. We just take and times those 2, and we get 5 moles of, and that should be NH3. Okay, that's what happens when you copy paste. The moles of nitrogen goes out, and we end up with how much we can make. Okay, just like a recipe, I can now know how many moles of ammonia I can make. All right, so first, did you take and balance this equation? Let's balance this equation. This is the one I did with the gummy bear. Okay, remember the gummy bear sacrifice we did? This is this equation. Anybody got it balanced yet? 2, 2, 3, yeah. And I think I've got it coming in, but let's see. Okay, how many moles of oxygen are produced? So here I'm looking for this in moles, and I always write it underneath so I know where I'm going. Okay? are produced by the decomposition of 6 moles. I put that underneath too. So I have 6 moles of this. I want to know how many moles of this I've got. Okay. This one I can probably just look at and see the ratio, but set it up. We start with the 6 moles. I want to get rid of the potassium chlorate. So potassium chlorate. So it's going to go on the bottom. So I put the 2 moles of potassium chlorate on the bottom. I want to get to oxygen, so I put 3 moles of oxygen on the top. The moles of potassium chlorate go out. I take 6 times 3 divided by 2, and I get 9, maybe, moles of O2. Whoops. Moles of O2. So I can see how much I can make. And that's assuming that I have excess potassium chloride. Well, we don't need excess, sorry. That's what we're producing. Sorry. Oh, come on. Ignore that. Doesn't want to do that. There we go. Okay. You need me to wait here for a minute? We doing okay? All right. Wait. All right, go forward. We're going to take that balanced equation, we're going to do some more stuff with it. Since we have now, we want to know how many moles of potassium chloride, whoops, I can spell moles, really I can, are produced by the decomposition of 3 moles of potassium chloride, or chlorate. So, start with what we're given, the 3 moles of potassium chlorate. Somebody tell me what's going to go on the bottom. Good. What's in front of the potassium chlorate? So 2 moles of potassium chlorate. What's going to go on the top? 2 moles of potassium chloride. So that's going to cancel out, right? These 2's are going to cancel, and the moles of potassium chloride are going to cancel. So how many moles of potassium chloride are we going to get? 3. Okay? So it's just a recipe. It's just a ratio. It's not hard. Kids start to freak out a little bit, but don't. It's not hard. Okay? Just think of it as cooking. All right. Next up. Remember when we did the molar mass per formula weight? Can you find me the formula weight of CO2? Do that really quickly. If you need a calculator, there's some up here. You're more than welcome to borrow them. We are going to need calculators out. You might want to get your periodic table out too, because unless you can see the periodic table behind you, you need it. How much? Good. That is right. So this is how we add it up if you've forgotten. And we figure out that's how many grams per mole. Now all this stoichiometry that we've been doing, this ratio thing that we've been doing, is great, but how do you measure a mole? How do you know how much a mole is, right? If I'm going to produce that much, I want to know how much that is. The way we can do that is through this conversion. So we're going to add another conversion in. We're going to find out how many grams that is. Okay, does that make sense? Because I can weigh grams. I know how much that is. It's like saying, I want a mole of cookies. I have 0.03 moles of cookies. I don't know how much that is, right? So, but if we can weigh it, we've got how much it is. So, remember our mole map? We're going to be coming here. The reason why I put that yellow, that mole, is because you have to be in moles to use the balanced equation to go back and forth between one compound and another, just like what we were doing. So here's my recipe, and I need to know how many eggs to how much flour. That's my recipe. But then once I find out how much flour, then I know how much weight 1 cup of flour weighs, and I can find the grams. So I have to stay in the yellow, going mole to mole, in the equation, balanced equation, but once I get what I want, I can change it to grams, or I can change it to atoms, but atoms aren't really helpful for me in lab. Okay? All right. So basically, this is a little bit more expanded version. It's still the same as that up there. We're not worried about volume yet. We're just worried about the top parts. So I'm going to go from moles to moles. That's our ratio that we've been setting up. And then I can go either mass or grams, or molecules or grams. Okay? That's a fancy, bigger way to look at it. Okay? So we have to use the balanced equation to go from moles of one thing to another. We have to use the recipe. Okay? So let's go ahead and balance this equation. Now let's see what we can do with it. We're back at the window. Back at the door. Are there no more left? Okay, I'll run down in a minute to get your one. Grab a piece of paper out and start writing. Did you not check in? No. Okay, I'll have to get you in a minute. All right, what do we get?
16, 12, and 10. I don't know if that's right.
Okay, do I have a second on that?
Can we simplify it?
Can we simplify?
Just divide it by 2.
Divide it by 2, yeah. And what's what we need to do? So what do we get? 1,
8, 5. No,
6.
no, 6 and then 5.
Okay, now does everybody agree? Okay, so now we look and see what we have. We have 1.5 moles of this. And it undergoes complete combustion. How many grams of O2? So here we got a question mark, grams do we need? Okay, what are we going to start with?
What you're given.
What we're given, always. And it goes up on the top of our T chart, our factor rating. What are we going to put on the bottom?
1 mole.
1 mole, you're right. What was in front of the thing that we were given? And we're going to put 1 mole of pentane. This happens to be pentane. What are we going to put on top? What am I trying to get to?
O2.
What?
Grams.
Grams, but I can't get to grams until I get to the right moles. So I am trying to get to O2, so I'm going to use the 8 on the top and put 8 moles of O2. At this point, I can cancel out moles of pentane. But I'm still not to grams. I need to do one more conversion. So I stayed in that yellow area. I've gone mole to mole using the equation. Now I'm going to come out and go to the right to get to grams. So on the bottom, I'm going to put 1 mole, maybe. And on the top, I'm going to go 2 times oxygen's mass, which happens to be 31.998. And I didn't show that off to the side because it's just 2 times oxygen's weight. Okay, at this point, moles of oxygen cancel out. Well, I did show it down here, down the bottom, underneath the subtitles are currently unavailable. I've got to figure out what's going on with that. Okay, and I just times to the top, and since the bottoms are 1s, I can ignore them, and I get that many grams of oxygen. So I need that many grams of oxygen to totally consume the pentane. Okay. Let's see. All right. You okay? Go forward. All right. So here we have that equation again. Combustion of pentane gas to get water and carbon dioxide. If I had 80 grams of, so I have 80 grams of CO2 produced, how many grams of, how many moles of oxygen were needed? So now we've got another problem. We're starting with grams. We've got to get it into moles before we can use the equation. Can't use the balanced equation or recipe till I get it into grams. It's sort of like being given a recipe and then being given all your equipment in metric and your recipes in English. You got to do a conversion first. Okay? So we're going to start with our 80 grams, but we're going to have to add up CO2. We've done that already. What was the mass of CO2? Do you remember? 44. Good. So we would have added it up, and we'd found out it's 44.09 grams in 1 mole of CO2. We want to get rid of the grams, so it's going to go on the bottom. We want to go to moles, it's going to go on the top. So just remember, what I want to get rid of goes on the bottom. What I want to go to goes on the top. Okay? Now, once I've got there, then I can use the balanced equation, and I can use this 8 and this 5. What's going to go on the bottom? That's 5, good, because I want to get rid of CO2, so I'm going to put the 5 moles of CO2 on the bottom. That will cancel out, and then I'll put my 8 moles of oxygen on the top. You see how this works? Okay. Now, this time I've got to be really careful. When I go to put this in my calculator, when I hit my divide sign, I need to make sure that this whole bottom part is in parentheses. If it is not, you're going to end up with a wrong answer. That is the biggest mistake I see kids make. Okay, that's the biggest mistake I see kids make. Right? So, we're going to times to the top, divide through by the bottom, in parentheses, and we get this many moles of O2. Everybody okay so far? Kind of. It's just adding on to what we've been learning so far. So going from grams to moles.
Where did you get that? You just pull up those.
So 80 came from up here already given, but the 8 and the 5 came from here.
So after you do like the regular.
So first I changed the grams to moles so I could use the equation. Then I use the numbers in front to change from moles of one thing to moles of something new. Okay? Good questions. All right, here we have that equation again. Question methane. This time, however, we want to produce 2.75 moles of water. How many grams of pentane do we need? Okay, go, guys, walk me through. What do I do first?
What you're given on the top.
Put what I'm given on the top. Set up my factor label. All right, now what? What do I put on the bottom? I look at the numbers in front. I'm already in moles, so I can use the numbers to go from moles of one thing to moles of something new, right? So what goes on the bottom?
6.
6, because I want to get rid of the water, right? So the 6 moles of water goes on the bottom. What goes on the top?
What you're going to.
Which is 1 mole of the C5H12, which is pentane. That way, moles of water cancel out, maybe. Come on. It doesn't love me right now. Okay, now, what do we do next? We've got to add up pentane, right? Because now I'm in moles, but it wanted grams. So I'm just doing my mole map from moles to grams. What goes on the bottom? I would do that when I went by. What goes on the bottom? Good. And then the mass that we added up goes on the top, and moles of pentane gets crossed out, and we're now in grams. We only have one number on the bottom because 6 times 1 is just 6, so we can go through the top and we can divide by 6 and we're done. Be careful, if there's more than one number on the bottom, you have to put it in parentheses. That's the big, big thing that you need to be watching for. We should end up with 33.06 grams of pentane.
Wouldn't be 0 second until you round up.
It might be. I usually don't mark you off if we're off by 1 in the end. Okay, let's go to the next one. This is the end of what I'm going to go through with you in class. The rest of your turn to practice and do. If you have questions, I'm going to use the red area as a help area. If you're getting this, move out of the red, let somebody else move in. It is an open movement. And if there's all 4 already and you still need help, bring a chair and sit by us. Okay? Any questions? All right. We need to send down to the copy center and get yours. So it's copying like crazy to try and get things done before class started.